Hello, AP Physics students, and welcome to Thursday. And in this edition of discussing magnetic fields with particles, we're going to be talking about the velocity selector and the mass spectrometer. So let's jump right into it. We talked about the forces that particles feel inside a magnetic field and the right-hand rule that came with that. But let's look at an interesting device here. If we have a little chamber here, and in that chamber, we have a magnetic field. Let's just say it's pointing into the page at this point. And then, right over here on the side, we've got a little hole on each side of this chamber that a particle could fit through, a small hole. And if we take a particle, a positively charged one, and project it into this device, then let's see what happens. So if we project it into this little chamber, we use our right-hand rule. We see that the magnetic field is straight down, the thumb is pointing to the right, so the force you would feel up. This particle would be bent up like this. But the problem is, if you do it like that, then you're not going to make it through the chamber. You won't make it straight through. So the first question is, which direction do we have to put an electric field so that it counteracts the magnetic field or the magnetic force? So if this particle is going to try to move up, then we need to have something that shifts it back down. And to shift it back down, we have to make the positive particle move down with an electric field. Given that positive charges move in the direction that the electric field points, this means that we're going to have to put an electric field pointing in this direction. So this is the electric field. So the magnetic field was the part that pointed in. The electric field is the part that points down. So now, if there were no magnetic field, the particle would do this. It would come down like this. But we're looking for the special condition by which this particle is going to make it straight through without being deflected. And if that's the case, this will happen when the magnetic force up equals the electric force down. When those two things are equal, then this particle will make it straight through. Now, if you remember from our lesson last time, the electric force and magnetic force, we know those. So the magnetic force we know, the electric force we know. The magnetic force is BVQ. The electric force, we know from before, that's charge times electric field. And what's really fascinating about this device is you can see that the charge cancels. It doesn't matter what charge goes through here. As long as it is charged, then you'll have it. So the magnetic force and the electric force would actually balance out. Now, in this case, though, that means the velocity is E over B. When you get a particle that moves through this chamber with a velocity E over B, it will not be deflected. It'll pass straight through. That's why this device is called a velocity selector, because you can adjust the electric field and the magnetic field, and if you adjust them to the proper ratio, you can get pretty much whatever velocity you want out of here. Now, if the particle goes too fast, you'll see that this side of the equation is too big then, because V is too big, and the particle will bend up here. If it goes too slow, then this side of the equation won't be big enough, and it'll bend down here. But if it's just right, kind of that Goldilocks speed, it'll pass right through. Now, what you may be surprised by is that the velocity of this particle, E over B, well, that E over B, if you actually do that, the units for electric field and the units for magnetic field, pulling that together will give you a unit of meters per second. It's one of those other bizarre things that happens with this, that the electric field and magnetic field divided by each other actually give you a unit of velocity. But this is a very useful device in particle physics because you can have something that passes straight through this chamber, and you can also dial the speed to whatever you want. These are particles you can't even see, but you know how fast they're going because you know the electric and magnetic field. And you can produce electric fields really easily by making parallel plates with voltage. You can have magnetic fields by putting a solenoid or some other device to create a magnetic field. So this is the velocity selector. The forces balance, and when the forces balance, that speed that you'll get the particles to come out with is E over B. But the velocity selector is only one part of a bigger device. And that bigger device is called the mass spectrometer. And in the mass spectrometer, we get something very similar. We have a part of it that is the velocity selector. Here's the velocity selector here. There it is. And we'll call that magnetic field B. And then we'll say there's an electric field pointing down. That's electric field E. And again, there's a little chamber that it's going to go through. The particle is going to make it through. It's going to pass right through because it'll have the specific velocity. But then over here, there's going to be another chamber. And in this chamber, we're going to have another magnetic field. Now this magnetic field is not necessarily the same as the first one, but it could be. But I'm going to call this B prime. Now, what happens in this in the mass spectrometer is you are able to sort out particles based on their mass. It's a fascinating thing you can do, and you can basically break down what a substance is. You put something in the mass spectrometer, you send it through by accelerating it through a voltage, and then it goes through there at a specific speed. Now we know that things that are going to go through the velocity selector part right here, the pieces that are going to go through the velocity selector, they're going to go through with a velocity E over B. We know that that's the case. We saw that in the last part of the problem. But then, once they get past there and move into the circular part of the chamber, they're going to be bent again. Remember, here, they were bent up, the particles, and then the electric field bent them down. But once we get to this section, there is no electric field in that section. There's only a magnetic field. So now, they'll just be bent up. And this particle is going to be bent. It goes straight at first, and then gets bent into some kind of circular pattern and gets over here where it hits the detector. Now, if we look at that, the only force that's acting on that during that time is the magnetic force. So the magnetic force must be the centripetal force, just like we saw when we just did the normal particle pieces in magnetic fields. So the magnetic force must equal the centripetal force. So BVQ equals mv squared over r. Conveniently, one of the v's canceled out. But this b, by the way, is b prime because we're on this side. So I can't make that mistake. Then what I can do is do a little rearranging and plugging in b prime times q times r equals m, but then we know that v has to be E over B. And we're starting to see a couple things here. We're starting to see that the radius is proportional to the mass. And that's important because we can sort things out in this regard. And what we're going to see when we pull it all together is that the mass of that particle that we have, the mass turns out to be B prime times B times Q times R divided by the electric field. That's going to be the mass of the particle. So again, B times B prime times QR over the electric field. But the important thing here, the main piece, is that the mass of the particle is proportional to the radius. So if I were to put a sample in here, which had many particles going through, some might be here, and some might be here. Things that have a bigger mass will have a bigger radius. Things that have a smaller mass have a smaller radius. And this is actually how you could do something like carbon date. Because what you can see is that carbon-12 and carbon-14 being the radioactive isotope, carbon-14 is heavier. And so because it's heavier, it will have a bigger radius. Carbon-12 has a smaller radius. So because of that, we can sort it out. And by seeing in the detector over here how much of each substance you have, you can actually figure out how old that substance is. Because once it has dead tissue, it's not able to keep the uptake of the radioactive part of carbon. So we really saw two things here. We had the velocity selector, which saw a particle pass through a chamber with a specific speed, E over B, and it's kind of amazing that E over B is measured in velocity. And then we used that velocity selector in the mass spectrometer so that we knew the speed that it came through, and then now it's bent into some kind of a circle, and we can figure out where it hits and what the radius and therefore the mass is. These problems are very, very common problems on the AP test. Why? Because they involve right-hand rules, they involve mechanics, they involve electric and magnetic fields in the same problem. So it's a very, very common thing for you to see. So now it's time to work on Unit 12's Worksheet 2 and work on problems 6 through 10. There's going to be some parts in there. We have to make some proofs as well. But time to go ahead and get started. Plus, there's a few videos to watch about why some of this works. And we will see you tomorrow. So happy Thursday.